we're looking at that today, geometric probability. But first, we need to remember what probability is. All right, so the probability of an event is defined by the number of desired outcomes over the number of possible outcomes. For instance, if I grab a bunch of markers, right? Here's a bunch of markers right here. We have 7 markers. You can see there's 7 markers, all right? There's 3 red, 2 black, 1 blue, 1 purple marker, okay? And say I put these in a bag and I shake it up and I reach in without looking and I pull one out, and if I'm desiring a red marker, well, remember I said there's 3 red markers. That's the number of desired outcomes. The outcome I would desire would be red, and there's 3 of those. And total possible outcomes, well, there's 7 markers I could have chosen, and I just happen to desire the red. So the probability of choosing a red marker would be 3/7. Well, the probability of a black marker, if I desired a black marker, well, there's 2 black markers out of 7. Continuing, there's probability for a purple. There's 1 purple out of 7 markers. And finally, there's also a blue marker, so the probability of choosing a blue marker would also be 1/7. And these are all the possible choices. Notice that 3/7 plus 2/7 plus 1/7 plus 1/7 adds up to be 1. The total of all the probabilities added up, all the possible events, is 1. That's 100%. Okay? There's nothing else that could happen. If you're going to choose a marker out of this bag, it's going to be one of these 7 markers. Okay? So a little bit more specific then. We're thinking about geometric probability. That's what we're talking about. So geometric probability is easiest to think of when we're thinking about areas. Okay, so let's think about a circle. As everybody has played some game where you have some kind of spinner, and maybe there is equal wedges throughout the spinner. Maybe there's not. So take a look at this spinner right here. It looks like there's 6 equal wedges, and if this really is 6 equal wedges, then we would know each one would have to be 60 degrees. Okay, because if every one is 60 degrees, they all add up to be 360 degrees. All right, fair enough. And I'm going to number these 1, 2, 3, 4, 5, and 6. Maybe this is the game you're playing where you have a spinner, numbers 1 through 6. Okay, I don't know what game you're playing, but this could apply to any game. All right. Now, if we wanted to know the probability of rolling a 1, well, you might say, hey Mitchell, it's going to be 1/6. All right, because clearly there's 6, and I can see they're all equal 60 degrees, and that's 1/6. Well, let's prove that with the area. All right, the spinner has the probability that has the ability to land in any of these 6 regions, and well, we know there's some kind of radius here. I'm going to let the radius of the spinner be, let's say, the radius is 2 inches, just for the fun of it. And we can see that this piece of the pie right here at 1, the area of that would be a sector of this circle. So that would be the area of our circle, pi times our radius squared, times the measure 60 degrees out of 360. And 2 squared, of course, is 4, so that's 4 pi. Square inches times a sixth, and 4 times a sixth gives us 2/3. So this is 2/3 pi square inches is the area of that sector. Well, what's the area of the whole circle? The whole circle, we found earlier, the area of the whole circle would be 4 pi squared. Okay, so the area of the sector, two-thirds pi. The area of the circle, 4 pi. And remember our definition of probability. The number of desired outcomes divided by the total number of outcomes. Well, in this case, the area of our desired outcome divided by the area of our possible outcomes. 2/3 divided by 4. Desired over total. 2/3 divided by 4, that's 2/3 times 1/4. That gives me 2/12, which comes out to be 1/6. And so in this case, we could see, because they're all equal, yes, it's 1/6. But this applies to any situation. So let's change it up. Let's make these sectors a lot worse. And by worse, I mean different. Okay, circle, let's do a weird chunk like that. We'll say that's maybe 120 degrees right there. We'll do a little sliver here. We'll say that's 28 degrees. We'll make a right angle here at 90. And 210. 38. I believe that leaves this for 122 degrees right there. Go ahead. Of course, we just made this up and we'll make sure it works. Because we know they all should add up to be 360. They do. Alright, so this is a possible spinner for us. Alright, some weird game you're playing where this is just slightly more degrees than that. Well, let's just do that. Let's compare the probability of getting 100, of landing in, so let this be 1, 2, 3, 4, all right? Let's compare the probability of getting a 1 to the probability of getting a 3. Okay, we're thinking about a spinner here. It's flat, you know. It's not equal. These are not created equal in this situation, all right? So we need to know the area of the whole circle. We need to know what this radius is. Let's just let it be 1. All right, so let radius be 1. So we find the area of the circle. We know the area of the circle is going to be pi times the radius squared, and the area of the circle comes out to be pi. Okay, so this one will be easy to work with. It's just pi. And we know to find the area of each piece, it's going to be the area of our circle times the fraction out of 360. So let's just find all of the areas, and then we can compare them. We can start dealing with it. All right, so our radius is 1. And so the area of this sector right here, area of this sector is going to be the area of our circle, pi times 28 out of 360. So that comes out to be 7/90ths pi. All right, so that's the area of that sector. Moving on to this one, this is going to be the area of our circle times 120 out of 360. 120 out of 360 is a third. This is a third pi. Up here at 90, well, 90 out of 360 is a fourth, so this is pi times 90 out of 360. that comes out to be a fourth pi. And down here, 122, this is pi times 122 out of 360. And that is 61 over 180 pi. So these are the areas of all the sectors. We've got the areas. These are not the probabilities. Let's create a little chart for us, the probability of each thing. Let's go probability of rolling a 1, probability of rolling a 2, probability of spinning a 3, and probability of spinning a 4. All right? Well, we know it is the desired divided by the total. Okay? So if we're looking at 1, well, the desired is a third pi, and we want to divide it by the total area, which is pi. Well, in this case, the pi's cancel out, we're left with a third. Spinning a 2. This is 1/4 pi, which is desired. If we wanted to get a 2, that would be the desired outcome out of the total pi. We cross out the pi's, we're left with a 4th. Down here, probability of spinning a 3, well, that is desired. Sorry, the area of spinning a 3 over the total. Once again, the pi's cancel out. We're left with 61 over 180. That is the probability right there. And finally, probability of spinning a 4, the area divided by the total area. Cross out those pi's and we get 7/90. And these probabilities are probably, fairly understood by us. But we look down at these 61 over 187 over 90. We'll change it to a percent if you need to. 61 divided by 180, change it to a fraction, then move the decimal twice to the right. This is about 33.9%. This down here is 7 over 90. That's about 7.8%. Of course, we know 1/4 is 25%, a third, 33.3%. And notice if we add these up, 33.3, 25, 33.9, 7.8, that's 100%. All right, this is everything that can happen is right here. Of course, these have been rounded, these that I had decimals, but the fractions keep exact probabilities for us.